Okay, so let me share my screen. So can anyone confirm that screen is visible? Hello, can you hear me? So can anyone confirm the screen is visible?
Yes, sir.
Okay, thank you. Okay, so today I'm going to start a new chapter. So till now we have been discussing about secrecy of a message, but I'm going to talk about message integrity. This is a very important topic, and message integrity or authentication code. So this portion here. Okay. So you might have heard about a couple of algorithms, or known as hashing algorithms, like MD4, message digest 4, MD5, okay, or SHA1. This is family of hash functions, SHA2 or SHA3. I'm going to describe one of them, especially SHA3 here. These are family of hash functions. Okay. And so what is data, data integrity? So what is data integrity? So basically, you can think like this, that many times you download a software exe file or executable file of a software from some website, right? Suppose on that server there is an adversary which is going to attach a virus on exe file, right? And so something has to be changed. I think you might have used this thing, like for example, you check the crc checksum and see that it matches. So normally with the exe files there is crc checksum value available, so you can actually match and see if that matches, that means it is authentic thing. Or otherwise, if there is a virus attached to it, so then this value will change. So then you know that it is a tempered file, right? And you will not handle that, you will not download that file. Similarly, if you are sending a message to your bank to transfer $1,000, say, or ₹1,000 to someone else, and you know and that message is received by bank, right? So but they want to bank wants to verify that it is you who are sending this instruction, so rather than someone else sending the instruction. So this message authentication or data integrity, is a very, very important task. How do we achieve this? So this is achieved by what is known as hash functions. Okay. So these are achieved by hash functions, and the kind of attack that is possible. So basically, suppose someone is sending data like x1, x2, say xn, and receiver. This is the sender, and receiver here is actually receiving. Say he or she may receive x1. So suppose these are bits, binary bits, right? So this will be, say, x2 bar, a complement thing, or flipping certain bits, or x3 bar, or say xn bar, right? So certain bits have been flipped. So now, how do we know that what was sent, right? So there needs to be some sort of checksum or something, which will make sure that what bits were sent. So this is known as bit flipping attack. Okay, so normally, in order to prevent these kind of attacks, what we do, so suppose x is some data. Okay, x is some data. Then what we do, we use a function known as hash function. Okay, and we compute y is equal to h of x. We apply this hash function on the data, and we get y. This is known as fingerprint. This is known as fingerprint or message digest. So normally, this is of say 160 bits or 256 bits, something like that. This value is hash function. So data is there. You compute the hash function, or basically this fingerprint, and you check. So basically, if x is sent, then you check the y. You check the hash function. Hash function value is normally uh, if hash if hash functions change. So initially, so basically one can send x and y both on the channel, right? X is actual data and y is your hash function. So now the receiver can check whether so suppose data is tampered and you receive x prime. So then what will happen? You compute the hash function. So hx prime will not be same as hx, right? Which is y. So it will differ from y. So this quantity, say it will, you will receive y prime. Y prime is not equal to y. That means data has been tampered. So you will identify the data has been tampered, right? So this is a very basic thing through which you can check if the message is altered or not, right? Now there are two kind of hash functions. So we can just describe, there are two kind of hash functions. One is keyed hash function. They are depending on some keys. We call it as keyed hash function. Okay. Uh, so basically there is a different hash function for each possible key. So there is a different hash function for each possible key, right? So a keyed hash function, uh, normally a keyed hash function is often called as MAC, message authentication code. Call it as message authentication code. When the hash function is keyed hash function, right? So for each key, okay. Suppose Alice and Bob are two people. Okay, Alice and Bob are two people, and they share a secret key k. Okay, so this key will determine a hash function h of k. Okay, so for a message x, so this is your hash function based on the key. Okay, depending on the key. So for a message x, the corresponding authentication tag, will be y is equal to hk of x. This is known as authentication tag. Authentication tag, or simply, it is also known as tag. So x is your message, and you compute this based on key. HKX is the authentication tag or a tag. Okay. So tag can be computed by either Alice or Bob. Both can compute the tag. And the pair x comma y can be sent over a insecure channel. So see, the objective here is not to actually protect the data. So we are not worrying about the secrecy right now. We are worrying about that the data has not been changed by anyone, right? that is our key thing. Data integrity is the main objective. So so sometime we can also have encrypted X and the tag. That is also a possibility. When both things are secure. Okay. So once you recover, so suppose X comma Y pair is sent over the insecure channel, and once you receive X comma Y, you check if Y is HKX or not. Okay. If it is, that means there is no tampering of the data is there, right? Otherwise data has been tampered. So you will be able to know this fact. Okay. So based on these discussions, I am going to define formally what is hash family. Hash family. Okay. So we have it's a 4 tuple: X, Y, K, and H. Okay. What is X? X is a set of possible messages. Okay. Y is a finite set of possible message digest. Okay. Or authentication tags. Authentication tags or tags basically. Okay. K is your the key space, and for every key in K, the key space, there is a hash function. There is a hash function HK in H. So H is a collection of hash functions. Okay. So each HK is a function from X to Y. Right. Okay. So now there are certain definitions I would like to say that. First of all, note that size of possible messages is finite or infinite. It could be both. It could be finite or infinite, but size of Y is always finite. Okay. Second, if size of X is finite and size of X is bigger than size of Y, okay, then the function is called compression function. Okay. In fact, we assume a stronger condition that size of X is twice the size of Y, bigger than twice the size of Y. Okay. So this is all about hash family. We can talk about now what is known as unkeyed hash function. A unkeyed hash function, okay, is a function h from X to Y. Okay. Or in simply, this you can think of it's a hash family with one possible key, right? So basically size of K is equal to 1. Okay. Message digest, I already mentioned what is message digest. So message digest for the output of an unkeyed function Okay. Output of an unkeyed function is known as message digest, and you know, tag, we use the word for the output of a keyed hashed function. Okay. Next, a pair x comma y in x cross y is known as valid pair under a hash function h, under a hash function h from x to y, right? If hxy is equal h of x equal to y, okay, then this pair is known as valid pair. So h here is, you know, keyed or unkeyed, doesn't matter, keyed or unkeyed hash function. Okay. So message digest for the output of an unkeyed function, tag for the output of a keyed hash function, you know. Okay. Okay. So now actually we are going to discuss methods to prevent the construction of certain types of valid pairs by an adversary, you know. So what kind of things are possible? Let me discuss. First of all, I would like to mention a few notations briefly, you know. Fxy y is set of all functions from x to y. Okay. If size of x is n and size of y is m, then size of f x comma y is m raised to power n. This is obvious, right? Any hash family f consisting of functions with domain x and range in y is basically a subset of f x comma y. So we call such families nm hash family. Okay, so this was all about basic things. So basic things about hash functions, hash family. So now the question is, if such a simple thing, that means if the data is given to you or message is given to you, just you compute, just hash it. So h of x you compute, you get y, right? And then you send the pair x comma y over in secure channel. After receiving the pair, you again compute, check whether y is equal to h of x or not. If it is not, so that means data has been tampered. So you know that, okay, that data integrity has been compromised, right? So you will be better careful to use the data. So now the question is, how do we design secure hash functions? So this is a big area, how to design secure hash functions, you know. So whether any kind of function will work or there are certain functions that we should avoid. So I'm going to discuss three problems which are very, very important. And if these three problems are difficult to solve, then the hash function is said to be secure. Okay. So these three problems are related to the hash function. So we are going to talk about security of the hash function. Security of hash functions. Okay. Security of hash functions. Okay. So suppose h is a function from h to y. It's a hash function. So let x is a element of x, okay, and define y is equal to h of x, okay, hash value of x. So the first problem that we are going to discuss is known as, I'll just mention problem 5.1. I'm just putting the same reference to the book. Preimage. What is preimage problem? Instance is given to you that a hash function h from x to y, and suppose y is an element of y, okay, find x, find x in x, find x in x, okay, such that h of x is equal to y. So kind of finding a preimage. So this hash function is given to you. Y is an arbitrary element of y. If you can find a preimage of small y in x such that h of x equal to y, okay, so then I think a hash function will not be secure if you can do it easily. So if it is difficult to find preimage, hash function will be secure, okay. So this is one problem, okay. Okay, so hash function is secure if we say that so a hash function for which preimage uh, cannot be solved is called one-way hash function. One-way hash function, okay. So you can go from x to y, but reverse is difficult, or it is also known as pre-image resistant. Okay, pre-image resistant, you know. So this is the one part. So security of hash functions we are discussing. The first problem is pre-image. Given a hash function h, an element in y, if you can find easily the pre-image, then the hash function is not secure. Okay. So we need to design a hash function in such a way that the problem solving problem pre-image is a difficult problem. Second problem, okay, second problem is second pre-image. Okay, so what is this here? Instance is given to you, a hash function h from x to y, and an element x is given to you. X is given in x. Okay. Now the question is find second pre-image. Find x prime in x. I am finding second pre-image in x, which is such that x prime is not equal to x. Okay, and hx prime is same thing as hx. So this is a second pre-image. Okay. Okay, so basically, you know, for some element y, you know, if x is first pre-image, if you can find second element for that hx prime is same thing as hx, so this is known as second pre-image. So if you can solve this problem easily, then also, you know, hash function is not secure. Okay. So I would say that we can circle it here. A hash function for which second pre-image problem cannot be solved efficiently is called second preimage resistant. And we want our hash function to be second preimage resistant, So we want our function to be preimage resistant. We want our function to be second preimage resistant, okay? Third problem that we would like to look at is known as collision. What is collision? So instance is given to you, a hash function h from x to y, okay? Find 2 points, x and x prime in x, okay? In x, of course, these are distinct points. Find 2 distinct points x and x prime such that what we have, that hx prime is same thing as hx. It's kind of collision, right? So that means there are 2 distinct points in x which are giving you the same hash value. So basically hash value is colliding, it's collision. That's why this name is collision, okay? So collision. So a hash function for which collision cannot be efficiently solved is often known as collision resistant. And we want our function to be we want our hash function to be collision resistant, So we want our function to be these kind of, so security of our hash function depends on these 3 problems. If it is difficult to solve these 3 problems for the hash function h, then our hash function is secure. The first problem is preimage. Given an element y in y, finding an element x in x such that h of x equal to y is a difficult thing. This is preimage resistant. The function should be preimage resistant, second preimage resistant, and collision resistant. Collision should not be there, okay? So I'm going to use a model through which one can analyze these 3 problems, okay? So and I think so we would like to see what is known as random oracle model. We'll analyze the 3 problems in random oracle model. This was given by Belair and Logaway. They gave this random oracle model, and it is, so we are going to analyze these 3 problems in this model. We can actually compute certain probabilities, and you'll see that what is the how much difficulty. In fact, I will show you in so by computing these probabilities, we will make sure that how to choose the h function which is secure. How many bits are needed for a hash function so that it is secure, okay? So before that, actually, I would like to give you an example, which will, so we want our h to be well designed, our hash function to be well designed, okay? So that means there should be only efficient way to determine the value of hx for given x, okay? Efficient way to find h of x from given x, Okay, so I'll show you one example where this is not the case so that you understand, okay? Example is h is a function from zn cross zn to zn integer modulo n, and it's a linear function, Our hash function h is a linear function defined like h of x comma y is equal to ax plus by modulo n. But what is a and b? A and b are elements of zn. So it's a linear combination of x and y, right? And of course, n is greater than or equal to 2. So now you see that this is a linear function. Now this hash function is dangerous hash function. Why? Because you see that suppose that two values are given. Suppose we are given the values that h of x1 comma y1 is equal to z1 and h of x2 comma y2 is equal to z2, right? I don't know what are the values of a and b, but I just compute these values. H of x1 y1 is equal to z1. I mean, suppose these two values are known, then if we take r and s to be elements of zn and compute h of r x1 plus s x2 mod n, I'm just taking linear combination for r and s of x1 and x2, comma, similarly I am taking r y1 plus s y2 mod n. I'm just computing these values. So this is nothing but, you can see that from this definition will be linear combination. So it will be a of r x1 plus s x2 plus b of r y1 plus s y2 mod n, right? After simplifying, this turns out to be, you can see that r times ax1 plus by1 plus s times ax2 plus by2 mod n, right? I'm just taking the rearrangement of the terms, right? Now this is nothing but r of h of x1 comma y1 plus s of h of x2 comma y2 mod n. So knowing the values of hash values at 2 points, I am able to determine it at other points. This is a dangerous thing, right? Okay. So given the value of h at 2 points x1, y1, x2, y2, we know its value at various other points without actually having to evaluate h at these points. I have not evaluated h at these points, but I know the value. So these kind of things may happen. Okay. So now I think I am ready to describe random oracle model, and I'll discuss how the ideal hash function should look like. Okay. So we'll call it as random oracle model. Okay. So in fact, I will use short form random oracle model. Okay. So it provides a mathematical model for an ideal hash function. We are looking at an ideal hash function. Okay. How the hash function should look like. So basically, there are certain assumptions in this model. So why, so that let us understand a hash function. So actually, we are not given any formula or algorithm to compute the values of h. Rather, I will say that a hash function h, from x to y is chosen randomly. Okay, from set of all functions x comma y, right? And we are only permitted, this is an important thing, we are only permitted oracle access to the function h. What does that mean? That means we don't have any algorithm or formula to compute the values of h. Rather, there is only one way. The only way to compute the value h of x is to query the oracle. That's all. Okay. So it is something like this. It's that we are looking at looking up the value hx in a Gantt book of random numbers such that for every x there is a completely random value. There is completely random value h of x. Okay, so this is what I mean roughly. What is happening. Of course, in real life, such things does not exist. But we hope that a well-designed hash function will behave like a random oracle. Okay, we hope that that is how the ideal function should look like. Okay. So now we are going to look at the security, and before that, because of these assumptions, our assumptions of random oracle model, I can talk about certain probabilities. So let me mention our first result or first theorem. I'll call it theorem 5.1. Suppose h is a hash function chosen randomly and suppose x naught is a subset of x and suppose size of y is capital M. Suppose that the value hx have been determined by querying the oracle. Okay, if and only if x belongs to x naught. Okay, then probability of, it's a kind of conditional probability that h of x is equal to y is 1 by m for every x in x minus x naught. Okay, and all y belongs to y. Okay, so this is obvious due to assumptions in random oracle model. Okay, and this probability is useful in proofs involving the complexity of problems in the random oracle model, right? So this is a conditional probability computed over all functions h that takes on the spatial value. Okay, so this is an important result. Once we have this, I can talk about algorithms. So in this random oracle model, this is an important result just to mention that. Algorithms in random oracle model. Okay, so we are going to study the complexity of three problems: the pre-image, second pre-image, and collision. So those three problems we are going to look at, and in fact I'm going to look at randomized algorithms. What do you mean by randomized algorithms? I think some of you may not familiar with, but I'll just mention briefly. Randomized algorithm, so they can make random choice. They can make random choice during their execution. Okay, those are random algorithms. A special kind of random algorithms is known as Las Vegas random algorithm or Las Vegas algo. Is a randomized algorithm. Okay, that may fail. That may fail to give an answer. That's okay. I mean, it may fail to give an answer, but But if algo does return an answer, okay, then answer must be correct. So this is known as Las Vegas algorithm. So Las Vegas algorithm is a randomized algorithm that may fail to give an answer. Okay. So it may terminate with a failure message saying that sorry, failed. I cannot find an answer. But if algorithm does return an answer, then the answer must be correct. So this is known as Las Vegas algorithm. Okay, it's a randomized algorithm. So randomized algorithms are the algorithms that can make random choice during their execution. Okay. Now I'm going to define another parameter known as worst case success probability and average case success probability of the randomized algorithm. Okay, so let me suppose epsilon is a real number between 0 and 1. Okay, a randomized algorithm has worst case success probability epsilon if for every problem instance the algo returns a correct answer. Okay, with probability at least epsilon. So a random algorithm has worst case success probability epsilon if for every problem instance the algorithm returns a correct answer with probability at least epsilon. Okay, that is worst case success probability. Another definition, a random algorithm has average case success probability epsilon. Okay, if the algorithm returns a correct answer averaged over all problem instances of a specified size is at least epsilon. Okay, so here it is averaged over all problem instances of a specified size. This is an important thing to observe. So note in this case, the probability that algorithm returns a correct answer for a given problem instance can be greater than epsilon or less than epsilon. Okay. Okay. So that is the case. Finally, we can define what is known as epsilon Q algo. So epsilon Q algo denotes a Las Vegas algorithm with average case success probability epsilon in which the number of oracle queries that is evolution of H made by the algo is at most Q. Okay, so then we call it as a epsilon Q algorithm. Okay, so I think this is the really the basic things. Let me now describe the first algorithm, the find preimage. Let us analyze that first algorithm. Okay, and I think that will be useful. So I think the first algorithm I'm writing for the preimage. Find preimage. So what you do? The values are h, y, q. Okay. So all these algorithms, we are going to evaluate hx for q values of x. So hx for q values of x in x. Okay. So find preimage. Choose any x naught subset of x, and the size is q. For each x in x naught, what you do? If hx is equal to, check this condition, if hx is equal to y, then return y. Sorry, return x. Yeah. Else return failure. Okay, so this is the preimage, find preimage randomized algorithm. So we are just checking for each x in x naught if hx is equal to y. If true, that is fine. We are returning x, the preimage. Otherwise, it's a failure. So now I think I can compute the average case success probability of this algorithm. So I think that's what is our next result. So useful. We compute this. Theorem 5.2. For any x naught subset of x and size of x naught is equal to q, the average case success probability of algo 5.1, the above one which we find preimage algorithm, is epsilon is equal to 1 minus 1 by m raised to power q. Proof is bit simple, so I'm just telling you the proof. Let y is an element in y which is fixed, and suppose x naught is equal to x1 xq. Okay, these q elements. For each I between 1 and q, let ei denotes an event that h of xi is equal to y. This is the event. Then using theorem 5.1, which we computed here, theorem 5.1, this one. Okay, using this theorem, I can compute the probability for h of xi is equal to y, right? For this event, I can compute the probability of ei. Since ei is an independent event, this value is 1 by m. Okay, for all 1 less than equal to I less than equal to q. Okay, so thus the probability of the complement event will be h of xi is not equal to y, right? Will be 1 minus 1 by m for all 1 less than equal to I less than equal to q, right? Complement will be 1 minus 1 by, because you have to subtract from 1, right? 1 minus 1 by m. Okay, so of course I should mention that ei complement is the event where hxi is not equal to y. Okay, that is ei complement. Okay, so therefore if we use if the events are even e to eq, right? I mean, these events are E1, E2, EQ, right? For each I. So I can actually use logical operation here. So the probability of E1 join or E2, okay, E1, E2 or EQ is equal to 1 minus probability of E1 complement and E2 complement and EQ complement. Okay, so this value will be 1 minus 1 minus 1 by m raised to power q, because this we have computed, right? So the success probability of algorithm 5.1 is constant for any fixed y, and and it is identical. So we have proved the result, right? So epsilon is 1 minus, this is our epsilon, which we wanted to compute. Okay, 1 minus 1 minus 1 by m raised to power q. Okay, so I think this was for the algorithm pre-image. The randomized algorithm is find pre-image. A similar result holds for algorithm 5.2, which I am going to briefly mention rather than going into details, but I'll just mention it here. Algorithm 5.2, which attempts to solve second pre-image, right? So for any, first of all, the algorithm is find second pre-image. Okay, so y is assigned as hx, choose x naught subset of x minus small x, size of x naught is equal to q minus 1, and for each x naught in x naught 2, if hx naught is equal to y, then return x naught, or otherwise return failure. Okay, and for this algorithm, we can mention the theorem directly without any proof now. For any x naught, there is everything is similar except minor change here. Okay, minus x with cardinality of x naught is equal to q minus 1. The success probability of algorithm 5.2 is epsilon is equal to 1 minus 1 minus 1 by m raised to power q minus 1, right? Rather than q, now we have q minus 1. Okay, I'm not proving it here. So I think that's all for today. Now we are going to describe the final collision things, and we'll discuss some of those things in the next class. I'll show you how the birthday paradox is related to our collision algorithm, right? So remembering that in the birthday paradox, we know that in a group of 23 randomly chosen people, at least 2 will share a birthday with probability more than half, right? So that is equivalent to collision problem. We are going to look at that problem in our next class. I think that's all for today. If you have any questions, please do ask me. So this is all algorithmic stuff. I mean the probabilistic stuff. So we are analyzing the hash function. This is something very, very important. Later on, I'll talk about iterated hash functions. So once we finish the probabilistic part, then we'll talk when we finish the analyzing of the random oracle model. Then we are going to talk about iterated hash functions, and then we'll give you the construction, especially to SHA-3. That's a very popular one. And then you'll see the importance of these results, there. Any question?
Sir, is there any update regarding project?
Okay, so I think regarding project, I am going to send you a list of possible topics, and maybe you can start working on it. Okay.
Okay,
So,
sir.
yeah. Yeah, you have. I think some people are doing projects already. They started, but I think others. I can give you a list of the projects. So that should be okay. Okay, so I think if there is no more questions, let me end all the stuff, and we will meet again on